LangChain, LangGraph, LangSmith. Three names you keep seeing in every serious AI engineering discussion right now. Not in research papers, in production, in systems that retrieve from real data, call external tools, run multi-step reasoning loops, and get monitored like actual software. But most people who have heard of them or even used them have a fuzzy picture of what each one does, why all three exist, and how they fit together. That's what this video is about. A ground-up breakdown of the entire stack, what each piece solves, how they relate, and how they combine into a coherent architecture for building AI systems that go well beyond a single API call. Let's get started. When you hit an LLM through an API, the interaction is dead simple. You send a prompt, the model returns text. That's the whole thing. Think about a simple document Q&A system. A user asks a question about an internal policy document. Before you even call the model, you need to find the right document out of potentially thousands. Then you need to construct a prompt that includes the relevant context. The model generates an answer. Maybe you need to format that answer or pass it to another step. What you have now isn't an LLM call. It's a pipeline. You're retrieving data, constructing prompts dynamically, calling the model, parsing outputs, and chaining steps together. And if you are building all of that from scratch, you'll end up writing the same boilerplate over and over again. That's the problem LangChain was built to solve. LangChain gives you the building blocks to structure applications around language models, rather than just treating them as isolated API calls. So let's walk through the key abstractions because each one solves a specific pain point. First, prompt templates. Instead of hard-coding prompts as static strings, you define reusable templates that inject context at runtime. Something like, explain the concept of so-and-so topic in simple terms. Your application substitutes the topic based on what the user is asking. Simple idea, but it means your prompts are structured, testable, and maintainable, rather than scattered string literals across your codebase. Second, chains. A chain is a sequence of steps where the output of one component becomes the input of the next. Summarize the document, extract key insights, generate a user-facing response. Each step involves the model, but they are wired together into a single cohesive workflow. LangChain handles the plumbing so you don't have to. And then there is tools. By default, an LLM can only generate text. It can't run a calculation. It can't check today's stock price. It can't query your database. Tools fix that. A tool is just a function the model can invoke when it decides it needs external information. The model says, I need to run a web search. The framework runs it, gets the result, and passes that back into the model's context. Now the model can continue reasoning with fresh, real-world data. This is the shift that turns a text generator into something that acts. Next up, RAG, Retrieval Augmented Generation. LLMs have a hard limitation. They only know what they were trained on. You can't retrain a model every time your company updates its internal docs. RAG solves this elegantly. Instead of cramming knowledge into the model, you store your documents in a vector database. So when a user asks a question, the system retrieves the most relevant chunks using semantic similarity search, injects them into the prompt, and the model answers based on that context. The model doesn't need to know everything. It just needs access to the right information at the right time. Now here's a problem that doesn't show up until you try to ship. Your LangChain agent can call tools, but the moment that agent needs to act on behalf of a real user, read their Gmail, post to Slack, update a Jira ticket, push a GitHub issue, you need OAuth. And not once, for every single provider your agent touches. Think about what you are actually building here. Your application kicks off an OAuth flow. That flow needs to handle three things that are all your responsibility by default. The OAuth handshake itself, storing and managing the tokens it gets back, and refreshing those tokens before they expire mid-task. And all of that produces a connected account, a live authenticated link between one of your users and one external provider. Then that connected account authenticates against the actual OAuth providers, Gmail, Slack, Jira, GitHub, each with its own token logic and scopes. Now multiply this by every provider your agent needs and every user in your system. Your LangChain tools request a token. You have to return tokens at tool call time via an encrypted token vault. so that the tokens live outside the model's context window, as there's a huge surface area for attacks and vulnerabilities. And this is what our today's sponsor ScaleKit offers you out of the box. Your agent calls a tool, ScaleKit handles the authentication, OAuth, token refresh, credential isolation. It enforces the access rules, delegated identity, per agent scoping, RBAC, and executes the tool call against whatever system you need, SaaS, API, MCP server, database, and logs every action, who, what, when, which agent. And you just focus on the agent and business logic while this unified gateway handles the messy complex stuff. They in fact support 3000 plus tools, Gmail, Slack, Jira, Salesforce, Notion, GitHub, and more. And if you need your own OAuth app credentials for production branding and higher rate limits, they support that too. Link is in the description. And once you have tools and chains working, developers naturally start pushing it further. What if instead of a fixed pipeline, the model could decide what to do next? That's an agent. An agent doesn't just answer one question. It reasons about a problem, picks an action, executes it, observes the result, and then decides what to do next. Over and over until the task is complete. The loop, called the react loop, reasoning and acting. It looks like this. You first analyze the task. What do I need to do? Choose an action. Which tool should I invoke? Execute it. Run the tool, get the result. Observe. What did I learn? Is that task done? Repeat if not. But here is where the engineering challenge hits. These workflows are no longer linear. They have loops, they branch, they call different tools depending on what they find. They have state, information that needs to persist across multiple reasoning steps. You're no longer writing script, you're engineering a dynamic, stateful system. Simple chains can't handle this cleanly, which is exactly why LangGraph exists. LangGraph takes a fundamentally different approach to structuring AI systems. Instead of chains, it uses graphs. A LangGraph application is made up of nodes and edges. Each node is a unit of work. An LLM call, a tool execution, a retrieval step, a custom function. Each edge defines how the system moves between nodes, and those transitions can be conditional. Here is what that looks like in practice. Say you are building a research agent. It gets a question, runs a web search, reads the result, decides whether it has enough to answer, and if not, it searches again with a refined query. That's a loop. It's not straight line, and a chain can't model it cleanly. In LangGraph, that loop is explicit. The reasoning step is a node. The search is a node. The do I have enough decision is an edge condition. The system loops back or exits based on state. Speaking of state, that's the other key idea. Rather than passing data manually between steps, LangGraph maintains a shared state object the entire graph reads from and writes to. Each node picks up the current state, does it work, updates it, and passes control forward. This makes the system auditable. You know exactly what information each step had, what it changed, and what triggered the next move. But there's a problem that doesn't surface until you actually try to ship one of these systems. When something goes wrong, and it will, you need to figure out why. Was it the prompt? Did the retrieval step pull the wrong documents? Did the agent choose the wrong tool? Did the model hallucinate? In a system with multiple reasoning steps, tool calls, and retrieval pipelines, the failure could be anywhere. And unlike traditional software, where failures are crashes, the failure mode here is often a subtly wrong answer. LangSmith fills that observability gap. LangSmith records every step. The input prompt, the model's response, which tools were called, what they returned, the retrieved documents, intermediate reasoning, all visualized as a structured trace. When something produces a wrong answer, you open the trace and see exactly where things went sideways. But observability isn't just about debugging. It's also how you get better over time. AI outputs aren't binary. A response can be partially correct, off-topic, or subtly misleading. LangSmith lets you build evaluation datasets and runs your system against them automatically, measuring accuracy, relevance, latency, and token usage. So when you change a prompt or tweak your retrieval logic, you're not guessing whether it helped. You can measure it. Same goes for prompt experimentation. Small wording changes can dramatically shift model behavior. LangSmith lets you run A/B comparison across prompt variants against the same dataset. So your iteration is systematic. And once you are live in production, it tracks latency, error rates, token usage, and tool invocation patterns under real traffic. Think New Relic or Grafana for distributed systems. Here is what this looks like end-to-end. A user sends a request, LangGraph determines the execution path, which steps to run, in what order, with what branching logic. At each node, LangChain components do the actual work: the prompt construction, the retrieval, the model call, the tool execution. And LangSmith records the entire thing: every input, every output, every decision point, every tool invocation. That's the architecture. LangChain is the vocabulary. LangGraph is the control flow. LangSmith is the visibility layer. Each one solves a distinct problem. Together, they cover the full surface area of building AI systems that actually work in production. Now, none of this means LangChain is perfect. The most common criticism you'll hear from engineers: the abstractions can be too heavy. When something breaks, you're often debugging through multiple layers of framework code before you even get your actual logic. For a simple one-step LLM call, the overhead generally isn't worth it. Just hit the API directly. There has also been a pain around how fast the library evolved. Teams that built on early versions found themselves refactoring when the API shifted under them. LangGraph was actually born out of some of this frustration. Instead of rigid chains, you get explicit graphs where the control flow is right in front of you. And LangSmith exists because observability was an afterthought in the original design. When your pipeline is a black box, you can't improve what you can't see. So, the honest take is, if you are prototyping something small, you probably don't need this stack. Where it earns its complexity is multi-step pipelines, dynamic agents, and systems you need to evaluate and iterate on over time. That's where these three pieces start pulling their weight together. A year ago, building with AI meant writing clever prompts. Today, it means designing systems with retrieval pipelines, reasoning loops, tool orchestration, and observability baked in. That shift is already happening. The engineers building the next generation of AI products aren't just prompt crafting, they are architecting. And this stack is one of the core foundations they are building on. If you want to go deeper on any of these pieces, RAG pipelines, agent architectures, evaluation frameworks, that's exactly what we cover in this channel. Subscribe and I'll see you in the next one.